Right, so in the previous lecture, we talked about a discrete likelihood example when applied to maximum likelihood estimation. This time, we're going to take a look at an example where we are dealing with a continuous likelihood function. So let's run through the problem. You have two runners, call them D and M, and each runner produces the following distributions for their finishing times. Both of them are Gaussian. D has a mean of 15, standard deviation of 1. Michael has a mean 17, standard deviation of 1.5. And in the game, you observe the finishing time of just one of the runners, and you have to guess who ran that time. So here is an example run of the game. So both the players ran, and they produce two times. One is TD, one is TM. And what you observed is one of them. You don't know if this is TD or TM. And your job is to guess if D or M produces the T star. And as always, the first thing we do is to reformulate the problem into maximum likelihood concepts. We have, let's see, observations, the models or guesses, and the likelihood functions. LL functions. In this case, the observation is the T star. Is the T question mark. I'll call it T question mark. You don't know if it's D or M. And you have two guesses. You can either guess if it's D or M who produced that time. And the likelihood function are these Gaussians. Let's draw them out. So let's see, probability that you observe this running time, given that the model is given that it was actually M who ran, would look like the following. So dx given theta. So I'm plotting the likelihood function over the possible values that can take. So let's see, for M, we have mean 17, standard deviation 1.5. So it would look like this, 17, standard deviation of 1.5. And then for, likewise, we have a second likelihood function. For Donovan, the likelihood function would be similar shape, but centered at 15 with standard deviation of just 1 second. Okay, now that we have outlined the ML concepts, let's apply maximum likelihood to figure out, to derive a strategy. Again, according to maximum likelihood, we guess the model that maximizes the likelihood function. Note that the x here, as a reminder, is the observed running speed. Let's do a run-through of the strategy. Run-through. So first, let's say we have observed this running time, 21.5 seconds, and we don't know who produced this one time. So according to maximum likelihood, well, we just have to compare we just have to look at the two likelihood functions and see which produces the higher number. So x equals to t question mark given d. Let's make up some numbers here. Likelihood function of m. Oops, sorry, I should have said that this is theta equals d. So for m, 21.5, somewhere around here. Let's plug this into the likelihood function and say this gives us the number 0.05. And if we plug this to d, 21.5, say, so this should be a higher number. So this would be 0.15, and 15 is much further away from 21.5, so we would expect this number to be lower. Say it's 0.05. So I just made up those numbers. So m 0.15, and for d is 0.05. And since this number is greater than that number, we then guess it was m. It was m who produced that number, 21.5 second. Okay, so that's nice. We so far nothing too different from the discrete case. But what is nice is that actually we can rephrase this strategy of looking up which likelihood gives the higher number into a much simpler one-liner. So first, let's draw the two likelihood functions onto the same plot. So I'll draw m first. M is centered at 17, if that's right. Yep. 17, and D is centered at 15. So here, 15. Again, the axes are t or x, the observations. The likelihood function is the y-axis. Okay, so to figure out an efficient rephrasing of the strategy, let's consider multiple runs of the game. If observation is 21.5 seconds, as stated before, we draw 21.5 here. We see that, well, the likelihood function is of the blue guy is higher than the red one. So we see blue is above red, and so we guess blue. Guess m. And okay, more formally, this is probability of x given theta equals m greater than probability of x theta equals d. Oh, and caveat, these p's are not actually probabilities. They are probability density function. If you want to know more about why we use this term for continuous probabilities, come to office hour. I can talk about this some more. Okay, so that's case 1. Case 2, if observation is say 15 and we repeat the same process, what we see is the red line is above the blue line, and so now you guess red, and red is D. So what have we noticed here? Actually, the strategy is can only have two patterns, because there are only two regions in the entire curve. It's either red is above blue versus blue is above red. Okay. And what are these regions? Okay. In what regions would the red line be above the blue curves? It would be anywhere up to here, right? In this case, red is always above blue. And in what regions would the blue be above red? Well, it would be in the regions here. And we notice that they are partitioned very nicely by just a simple threshold. Let's call it T star, which is the intersection of the two curves. And so an equivalent strategy, a nice way of reformulating whatever we just found through maximum likelihood, is the following. 1, we find T star, which is the intersection of the two curves. Intersection of two curves. And then the strategy boils down to the following. If the observation is greater than t star, we guess, we guess blue, so we guess M. Else, that means t star at t question mark is less than t star. And so we guess D. Simpler. Much simpler. So compared to the, let's use the 21.5 second again. Now the decision making process is we see that 21.5 second is greater than t star. Let's say it was like 19 second. And so guess M. Easy. There is no need for us to take a look at the probability density function curves anymore. Right. Let's recap. In this lesson, we discussed a continuous likelihood function, well, two of them, and then we found out that the maximum likelihood approach applied to this problem results in a very simple strategy, whereby you guess hypothesis 1 if the observation is greater than a threshold, or guess the other model if the observation is less than a